Okay, let's start. Last time, I think we stopped at this point. We talked about auto, C++, 11 features. We use auto a lot with the iterators because typing all that name, the vector and an iterator as a type is kind of difficult and it is not that readable. This is much more readable. And the other thing that we use is the initialization, C++ container initialization syntax. Okay, we can do this kind of stuff in C++ 11. You can do the same thing as you can do the same thing with the arrays starting from C, but now I can do the same thing with the containers, such as the vectors or the sets or maps, or etc. And in your homework number 4, I guess, you are going to do the same thing. You are going to initialize your set of day year class with this kind of syntax. Okay. So let's move on. At the end of, remember what we said before. We said that at the beginning of the chapter. We said that. Okay, we said that we are going to look at the iterators, we are going to look at the containers, and the last one was the associative containers, and we are going to look at the end generic algorithms. So these will be about global functions. Okay, so let's go there. I think it was 36. Yeah. So I am not going to talk much about the efficiency, but just a small introduction, because this efficiency is the topic of data structures and algorithms course that you are going to take next semester. Okay, so we are going to talk about this running programs. How fast a function, how fast a piece of program. We really wonder about this. We like to have some kind of a measure, so that let's say I have my algorithm 1, my algorithm 2, they are doing exactly the same thing. They are, for example, making a search. I like to compare this in terms of their running times. Okay, what is the running time of algorithm 1 and what is the running time of algorithm 2? And if one of them is greater than the other one, maybe I will choose the smaller running time algorithm. Okay, so you might say that, well, it is easy, just implement it, okay, the best way possible. Compile it, run it, and measure the times, and that will give you the answer, right? Just implement it and measure the times. But no, I want to do this without doing the implementation. I like to do this during the algorithm design phase without implementing anything, because implementation is something expensive. I don't want to implement something that's going to be very, very expensive. Okay, so can I do this while I am designing the algorithm? The answer is yes. There are ways of doing this. It is not going to be exact, it is not going to be perfect, but it will give you some good idea. Okay, so that will be the discussion next semester. I will not talk much about it. For example, you can do this: implement it and run it. Okay, implement it and run it. Efendim?
Hocam günaydın.
Günaydın.
Tamam, Mustafa Hoca ben nasılsın?
Şükür hocam, iyiyim hocam. Acele değilse dersteyim bir. Çıkınca arayayım ben sizi.
Tamam hocam, peki çok sağ ol.
Teşekkürler. Did you get your homework number 4 and 5? Yes. Okay. Okay, so these are the numbers. So by looking at them,
Hocam hemen güncelliyorum şeyi.
biraz da zaman verelim, olur mu?
Tamam olur hocam. Fazladan zaman.
Okay. So he's going to give you some extra time. So by looking at these numbers, I don't have a single number. I know it is for 10 numbers, it is 2 seconds. For 100 numbers, it is 2.1. Then maybe I should draw these kind of graphs, right? So the algorithm one is, this is the number of inputs. Let's say number of inputs, okay, is the number of integers that you are going to sort. Let's say this is a sorting algorithm. For 10 numbers, it is 2 seconds, 100 numbers in this. Let's say one algorithm is behaving like this. It's a linear increase. When you increase n, you are going to increase the running time linearly. The other algorithm is doing, okay, the other algorithm is doing this quadratically. So it is, let's say this one is t is equal to n, and this one is t is equal to n square, and maybe there is another one, maybe this one, like that, okay. In this case, t is equal to square root of n. Which one would you choose? I mean, by looking at this, of course, I have some constants in front of them. These are not exact graphs. Which one would you choose? Okay. By looking at these graphs, this table will not make much sense because it doesn't give you one single number, and one single number doesn't work. Usually we try to prefer this kind of, the black kind of algorithm black, okay, because if you increase n, the t increases proportional to the square root of n. It gets very, very efficient when you increase n. This one is it grows quadratically. It decreases very, very fast, and this is it's a bad algorithm, not very bad algorithm. It's a bad algorithm. This one is nice, but the nicest one is this one. So you are going to make this kind of calculations, estimations before implementing your algorithm. Okay, there are some algorithms that behave like this, even worse than that. Okay, it is like this: t is equal to n factorial. Okay, or 2 to the power n, or n to the power n, and etc. That kind of stuff. Okay, so sometimes you say that there is no way that. Okay, so if I give you a set, let's say you have a set of n elements. How many subsets do you have in this set? How many subsets? 2 to the power n subsets, right? The algorithm to list all the subsets of a set cannot be lower than this cost. Okay, you cannot do it in linear time. Okay, because you need to at least iterate them one by one. So you are talking about t is in this case 2 to the power n, and 2 to the power n is a very bad number. You know that, right? It's a very bad number. Okay, and this is what is my favorite class? Class A. This one my favorite class, right? What is my favorite number? Did I tell you about my favorite number? My favorite number is this. Okay? This is my favorite number. This is the number of atoms in the observable universe. Okay? We have this many atoms in the observable universe. I am not talking about the world. I am not talking about the sun. I am not talking about the solar system or our galaxy. I am talking about the whole observable universe. This is the number of atoms that we know. Okay? So if you have an n, okay, in your set, if you have around 200 elements, okay, 2 to the power 20 is comparable to this number. 200, 2 to the power 200 is comparable to 200. So in your set, you have as many subsets as the number of atoms in the universe, right? So this number is a very bad number. When you grow n to 200, 200 is a small number, right? It grows very, very fast. That's what I'm trying to say. So don't forget this class. Don't forget this number. And what is my favorite color? I guess nowadays it is green. I don't know why. I don't have an explanation for this. Okay, so sorting program, okay. Sorting program, we talked about that, and we do this kind of stuff most of the time. We say that actually these blue ones, blue one, blue one, blue one, they are like in the same class. Okay, they increase linearly, but this one is proportional to the n square. So at the beginning, maybe it is doing a little bit slow with the problem n small, but later it's going to be fast. Okay, so with the containers, usually they give you this kind of numbers. They say that, okay, let's open up some. Let's open up some container stuff, PP and CPP reference, STD find. Let's see what kind of STD find runtime complex it has. Okay, STD find parameter return complex value. Okay. At most n applications of the predicate. It says that order n. When you do this with a container of size n, okay, I am going to make at most n comparisons. Okay, it's a linear time thing then. Okay, that's STD find. How about, can I do a binary search? Can I do a binary search in this? Yeah, there is a binary search in standard library. I didn't know about, no, most probably I knew, but I forgot. Okay, the binary search, remember, you need a sorted list, sorted vector, whatever. Okay, and it will work on it to find the target value. Let's look at the complexity. What does it say? It says between first and last is going to be log last minus first, so log 2. So the logarithm of 2 of n plus O1 comparisons. So it grows logarithmically. It's very nice. It is very, very nice. Which one is better, logarithm or square root? Which one would you prefer, logarithm or square root? Yeah, logarithm works better. It gets very, very slow. Okay, it grows very, very slow. Like that, it almost becomes like a flat line at the very high numbers. Okay, so we like these kind of algorithms, and binary search is that kind of an algorithm. So when you look up some algorithm, just check the complexity part, and it will tell you about the stuff. Okay, let's go to sort. Okay, sort, and let's see the complexity of it. The complexity is going to be, okay, n log n. Okay, n is the number of elements, log n. So it is worse than the linear time. Of course, you are going to check each element one by one. That's the linear time, and log n is this one. And this one says that n log n is the comparison on average. It looks like after that, after C++ 11, it says that it is n log n. It's not average. It is the exact time. Whatever you do is n log n. Okay. So I am guessing that this was quick sort, because quick sort behaves this way. After that, they converted everything to merge sort. Merge sort guarantees that it's going to be n log n. Okay, that's the complexity, but there should be some place where the memory requirement, how much memory it uses. It doesn't talk about memory. Usually this the complexity of the second one, the merge sort, is it requires order of n more memory than whatever you have in your array. So this one can sort in place without needing any more memory. If you have a array of size, let's say 1 million, it can sort using that 1 million positions only. This one needs 1 million more memory to make the sorting. Okay, so maybe there is a way to switch to other way. I don't know. So as I said, I don't want to talk much about this because this is the topic of the next semester. But just made a small introduction to this kind of analysis. We do this kind of analysis for the memory requirements too. Okay. By the way, O1 is O1 or constant time. Constant time is this. We like constant time running algorithms. We like this. Okay. Whatever the problem size is, okay. For example, give me the 712th element of your array. It is constant time. Doesn't matter how many elements you have in your array, right? So an index operator is constant time thing. Okay, index operator is constant time thing. Remember the hashing? Hashing can do the searching in constant time in O1 time. Okay, can do the insertion in O1 time too. It's very, very efficient. Okay. I told you about this just because you can understand what these are and try to imagine what kind of complexities they have. When you are making a decision, just check this complexity part too. And I wonder why they don't have a memory. No, memory. Yeah. See, this one say that I can throw a bad log, so you should maybe you should use this function in a catch try block, but no, it doesn't talk about the memory requirements. Maybe it is somewhere else. Maybe this documentation is bad. I don't know. Go back and let's look at some of the. We like this one. This is good. This is better than ON. N square we don't like. N log n is not bad for sorting algorithm. Okay, so let's look at some of the functions that we are going to look at. Okay, a vector of characters, and using this get function of Cn, I can get the. I think I can get the characters one by one. So I'm getting the characters one by one, and I'm putting it at the end of this line. Okay, and generic find function does that. Okay, give me two pointers, two iterators to make a search between. Okay, so beginning of the line and ending of the line, and this is my target. When I find that, I am going to give the iterator to that position. If I can't find it, it is going to be what? It's going to be. So what would you return if you can't find this one? It returns an iterator, right? You might say that if it's a pointer, you might say that it returns a null pointer. But this is not a pointer, it's an iterator. So what would you return?
Exception?
No, exception is something. Well, exception is part of life here. I mean, if you throw an exception, that would be against the logic of the exception. And in this case, it's not an exceptional thing, right? Either I find it or not find it, part of the algorithm. What would you do? Yeah. Yeah. It is just line.end, right? I would return line.end. That's what we did with the. I think we use this one, right? Find on a vector or on something. Or map, maybe, yeah, right? Map. I think we did that with the maps or sets. Yeah. Yeah, I think it returns line.end if it doesn't find it. Otherwise, it returns the found position. Okay, and another constant iterator here from beginning to the end. What does it say? Okay, line begin and okay. So you guys understand what it does? You entered before this. Well, in this case, what does it do? Yeah. This one, do you understand what it says? It finds an E, okay, tries to find an E. This one returns an iterator to the position of E, And this one will run a loop between the beginning of the vector until where you see E. If you didn't see E, it's going to be line end. It says that you entered the following before you entered first E, okay? So if you didn't enter it, it's going to print everything on the screen because you didn't enter it. And this is after E, right? Okay, so it's a generic find function. And this find function works in what time? O. If I have n elements in my vector, how many comparisons do you think I would make? If this is my n, if this is my t, what kind of function would be the running time of this find function? It's going to be linear time, right? So because if I have 100 elements in my vector, I will have to do 100 comparisons at most, right? So it's going to be linear time. It's going to be this function will be linear time. Okay? So I would expect that this part of the code, if it runs in around, let's say 100 seconds, this part of the code will be around 100 seconds too, because this part will find E. If E is not there, it's going to check all the elements, and these two loops will print all the elements on the screen, so this is kind of comparable. You understand what I mean by algorithm analysis, right? Before you do this kind of coding, you can guess what kind of running times you are going to get out of your pieces of your code. Also, what kind of memory you are going to use for those parts of your code. Not much memory other than the line. Not much memory other than the line. Okay, good. So that find was a constant algorithm. It didn't change anything. Let's look at some sequence modifying algorithms. Set algorithms, for example. Sorting sets, merging sets. Okay, this is the sort algorithm, merge sort that I told you before. By the way, there is a theoretical limit that no sorting algorithms can do better than n log n. That's the theoretical limit. For a general case, you cannot sort better than n log n. There cannot be any O(n) complexity sorting algorithm. The reason is this. Let's say I have n elements in my, let's say I have n elements in my vector, and I like to sort this one. So how many different combinations of sequences can I have for this n? Let's say I have the 3 elements, 3, 1, and 7. Well, it could be, okay, 3, 1, 7, 3, 7, 1, 7, 3, 1, 7, 1, 3, 1, 3, 7, and 1, 7. That's it, right? These are all the combinations of, these are all the permutations of these 3 numbers. So out of these, I think I am looking at this one, right? I like to find this one, right? This is 137. This is the sorted version. Out of all these possibilities, okay, out of all these possibilities, I am trying to find this one, 137. So how do I get back to this one? I used a comparison, right? I compared the first element with the second element, then the second element with the other element, and etc., etc. Whatever you do, you need to compare elements with each other. You need to compare elements with each other. And at the end, you need to end up with this one. So it's going to be like this. Compare these two, compare these two, compare these two, and this one, and maybe this one, and at the top you do this. So I am comparing 2 elements. Either I am going this way or this way. If I go this way, I am comparing 2 elements this way or this way. So my path is at the beginning is going to be like that, and I find it. So how many comparisons I should make? I should make 1, 2, and 3. 3 comparisons should be enough to end up at this position, right? Okay. So How many possibilities are there at the lower end? There are n factorial possibilities, right? If n is 3, n factorial in this case is going to be 6. There are 6 possibilities, right? To be able to reach one of these 6 possibilities, okay, there is one theorem that says that you need to make, okay, it is called Stirling's theorem, okay, it will tell you you need to make n log n comparisons. You cannot do better than that. So this is a tree, the height of the tree has to be n log n on the average. Okay, so there is a proof. You're going to look at this proof more carefully next semester, but you cannot do better than that. And merge sort algorithm does that, but there is a catch though. It uses extra memory of size n. Okay, good. What did I, oh, this is something different. I'm going to skip this one. What? Okay, I'm done. Yeah, okay, good. So sorting algorithms do that. Let's see what kind of other algorithms I have with me. Let's, okay, where is it? This is sort algorithm library. Let's go to algorithm library. And these are the stuff, okay? As you see, it's a mess. C++ 11s, C++ 20s, C++ 23s. Did they list C++? Whatever, okay? These are all search. Search is one of them. Here it is. Search and search is a range of a number for a consecutive copies of an element. Okay. Did you understand what I say? Okay. Find this one, but find it this many times, right? So, it says, give me the iterator of the first, beginning of the container address, end of the container address. This is the size, how many of them you like to find, and this is the target that you need to find, right? That's how it works. Let's see one example. Search, okay, forward iterator, forward, oh, this is the implementation of the search, the whole thing. Nice. It's a possible implementation. Okay, my first iterator, last iterator, count and value, and count is less than first. If count is 0, less than or equal to 0, then return first, my iterator. Otherwise, from first to last, it looks like it's going to increment first. See, it doesn't care what kind of iterator it has. Just one forward iterator. If it's a vector iterator or a list iterator or map iterator, doesn't matter. I am going to do this. If first is value, not value, then continue, do this. Otherwise, forward iterator candidate is first. For size, you understand what's going on? Size current count is 1 true, plus current count. Current count is less than return candidate success. Is this recursive? No. Did you guys understand? Once I find it, I change my candidate, forward iterator candidate to first. Okay. And size is current count 1 to plus current count. This is always true. Okay. If current count is greater than count, then I will return candidate because I found it. Otherwise, I will increment first my iterator. If first is last, then return last. If first is not value, then break 2 five in a row. I couldn't find it. Okay, so you remember the definition of this function. It finds 1, 2, 7, 7, 7, 5, 7, 2. Okay, so you are going to say, find me 3 sevens. Okay, that's what you say. Find me 3 sevens. So you are going to give 3 here for the count and 7 is there, right? And I wonder why. Oh, okay, this is a constant reference. Okay, so what do you think the runtime of this function is? How many comparisons would I make at most? Is it more complicated than the regular search function? Not search and, but search. No, right? It is exactly the same thing, ON. Just a different thing. It is ON. And let's look at another one. The first version, third version, what happened to the second version? There's another one. Example is using it. See also. How about the complexity? Okay. At most dot first applications, at most last minus first applications order n. So this is search n. Okay, it was available from the C++ 98. How about the ranges search? Which did I? What is the difference between these two? This is a template. With the C++ 20, they are introducing some other new mechanisms of writing functions. So this one is using that one, ranges search n. Okay, so these are for searches, finds. For each is interesting, we talked about that. For each of this container, do this and this and this. Okay, and countf. Let's look at this one. This one is good. Okay, count and countf. Let's see an example of countf. Countf. An array. Okay. STD array. Not classical array, but STD array. What is that guy doing behind his bag? Is there a person behind that bag? Big bag? Yeah. Is he sleeping? What is he doing? Put that bag just on. Yeah, okay, good. Thank you. Okay. So I have an array. It's just STD array, not vector, but array. The difference between array and vector, we talked about it yesterday. And what? Okay, so copy. You can guess it, right? From V begin to V end. All stream iterator. Did you understand what this line does? This line? It copies something to something from beginning of this vector to the end. Copy this to some other iterator, modifiable iterator, but that iterator starts at where is Abdurrahman when you need him?
Does it print them?
What?
Does it print them?
Yeah, it just copies all the elements of that vector to see out stream, all stream iterators, okay? See out. Okay? So it looks like there is a all stream operator function like this. Okay, it gives you an iterator to a stream, outputable stream, and in this case I am using a cout stream. It could have been a my file stream, okay? And this one is const int target. Well, here it is nice. I put the C++ 11 initialization curly braces here. And this one is, okay, this is counting. How many targets, did you understand this code? Maybe I shouldn't talk in English or Turkish. Just read the code and understand it. This is my first array. It looks like it is going to find this number, and this number inside this one. Okay? This happened this many times in this array, right? 3, 4, 5. I don't, well, okay, this one kind of does the same thing with the count F. Count just counts the number of occurrences of this 3 or 4 or 5 inside it. But now I am using this count F. Count F is saying that count the elements of that vector if this piece of code returns true for you, okay? So it's a lambda expression. Like a function, it's called lambda. Like a function, it takes a parameter, okay? If that element is divisible by 4, then I'm going to count it. If this returns true, then I'm going to count it. So it's going to probably will give me 1, 2, 3, 3, right? Count F. There are 3 elements of that array that are divisible by 4. This count F. That's the difference. Okay, the distance, auto distance. Okay, good. Distance is a lambda expression again. Okay, it's a function. I just defined it, right? From first to last, and I am going to count the first to last. Okay, and return true always. Give this one. This is my parameter, and return true. So this one is going to. This one, I don't understand what it does. No, I don't know what it does. Simplified version of distance with ON complexity. The distance, I don't understand what this code is, but I don't know what distance does. I guess there is a function named distance. I don't know. You look it up. Simplified version of distance with ON. Distance is an, okay, it's an iterator from first to last. First to last. First is, what is first? Oh, okay. First to last is given thing. The first, last, turn true. Okay. Okay. Beginning to the end. I don't understand, no. I don't understand what's going on in there. Anyways, so there are as many functions as you like, or more than as many functions as you like. In this case, some of them are non-modifying, some of them are modifying, copying, moving stuff around, transformations, swapping, reversing the arrays and containers, and the nice thing is they all work for all kinds of containers. Of course, appropriate containers. Okay, appropriate containers. Okay, as you see, maybe more than 100 functions, okay, are available. So if you need to do something standard, something you think that somebody might needed it before you, okay, just check this documentation out, see if the function is available, then use it. But you need to be careful about this C++ 17, C++ 20 things, the versions. If your compiler doesn't support that, then use them. Or if you are concerned about compatibility, okay, don't use anything later than C++ 14 maybe. Okay, good. Any questions? Wake him up. Okay, so if there are no questions, I'm going to start a new. I'm not going to start a new chapter. I will talk a few about I will talk about a few things I think our book did not cover. The first of them is going to be this smart pointers. Okay, so I have stolen these slides from this university, USC Viterbi University. Okay, it's called smart pointers, and I think I'm going to give you a homework about this, just to use the smart pointers. Smart pointers are usually, if somebody calls something smart, okay, smart homes, smart cars, It is not the home is smart. It is the seller of the home is smart, right? Usually, home is a home, right? Or the car is a car. But the smart pointers are really smart. So you are going to see why, and you are going to maybe get mad at me because why didn't you tell us about this before you tell us about the pointers? Because this is a much smarter way of using the pointers. You might be right, but I mean, we like you learn the basics of the language. This is a very nice tool. You should always use them whenever the pointers are usable, most of the time. That will make your life a lot easier. So plugging the Lake Smart pointers. So C++ 11 afterwards. But before the C++ 11, there were some libraries available to use these smart pointers. C++ 11 made them kind of smart standard. Okay. So the Boost library is the most known, most widely known library about that. Okay, let's look at this one, this code. Class thing. Oh, okay, this is my favorite class, right? The only thing is that its name is wrong. Okay, class thing. I have a thing object. I have a thing pointer. And of course, I could say that reference PTR, right? That reference PTR, because can I say this? Start T1. Can I write it? Start T1. Start T1. Can I write star PTR?
Yes.
Yeah. How about start T1? I can't. Why? Why? Because
It's not a pointer.
what?
It's not a pointer.
No, that's not the correct answer. Correct, of course, I can't, but I can't because
Dereferencing. Dereferencing. Dereferencing.
no. I can't write star T1 because
Not overloaded.
it is not over. So you wake up? Okay, good. Just not overloaded. Okay. Because the referencing operator is not overloaded, right? That's the correct answer. That's the correct answer. I can't write that, but I can always overload this dereferencing operator. I can overload that arrow operator. I can overload any operator that is needed by a pointer. So let's write a dumb pointer class. It's not smart pointer, just a dumb pointer. Okay, this is this templated class. Dumb pointer, star T star P is my private data member. This is my constructor. I just copy it. This is my star operator. Well, just operator dereference, just do this. Operator arrow does return the pointer itself. Remember, I can increment pointers. Well, if somebody asks me to increment something, I would increment it and return it. That's it. Let's use it. Okay, let's use it. I have some array of size 10 integers, a dumb pointer of integers, PTR data. So I initialize this, whatever I have inside this PTR, it's an integer pointer, right? I initialize with this one, and then I can do this in a loop from 0 to 10, increment PTR, and dereference it. So this PTR is of course not a pointer, right? It's an object of this dumb pointer class. So see, I wrote a class that behaves exactly like a pointer. So that's nice as an experiment. That's nice. Why did I write it? Why this doesn't make anything easier for me because I already have the pointers. I could have done this without the dumb pointer class. That's why the name is dumb pointer. Okay, that's why the name is a dumb pointer. All I'm saying is that I can overload the dereferencing operator, arrow operator, plus plus, minus minus, or less than greater than operators, right? Whatever you can do with a pointer, you can overload it. We can do it with the dumb pointer class. Let's make this class a little bit more intelligent, smarter, a little bit more useful. Okay. And I'm going to call it a unique pointer, useful, okay, unique pointer. See what I did? Let's make this a string. And new string. And PTR, maybe I should, what can I do with a string? I can do stuff like PTR, okay, get size, or PTR. What can you do with a string? Size, maybe. Let me do this. PTR, it points to a string, size. It will return with the size. Maybe I should just make it a little bit smaller and see out. Okay, so see, I make a new string, right? I make a new string, and I store the pointer of that new string in my PTR. My PTR keeps it. I can do whatever I want with that string, okay? Or I can do stuff like this. Why am I doing? Okay, I can do stuff like cout the reference PTR, right? The reference PTR will return me this one, the reference string pointer, and this will print the string out. Okay, good. The question is this: do I need to delete this string? Okay, do I need to delete this string that I made? The answer is no. Why not? Because this unique pointer class, whenever it dies, this PTR, whenever it dies, it calls the destructor, and destructor deletes whatever it is holding, right? So I made a new pointer, I made a new object in my heap using the new operator. I stored it somewhere in my local object. PTR is a local object, right? PTR is a local object. So what? I use the local object like a regular pointer using the dereferencing operator or the arrow operator or the plus operator, whatever. Then when I am done, this PTR has to die because it's a local object, it's an automatic object. When it dies, it kills the pointer it carries with it automatically. So this is a little bit more useful pointer class. In fact, it's very useful. Okay? If you are going to use a pointer, if you are going to use the new operator somewhere, then use this unique pointer class. But in fact, this unique pointer is defined in the standard template library. And let's go to that actually. Unique PTR. Okay, unique PTR is under the STD standard template library. You can have unique pointers of anything, and there is a oh, this is a lengthy one. Should I show you that? Maybe I should. Okay. No, well, I don't want to. No, don't show this one yet. No. Okay. So the unique PTR is something that you can use with any class that you have, starting from C++ 11. I can have unique pointers of anything. Unique pointers of anything. The nice thing is that whenever that pointer dies, it kills the pointed thing. That it carries with it. Okay. Good. So, but there is a problem with this unique pointer thing. The problem is this, okay? Let's write some code with the unique pointers. But before that, I think I need to take some break. Any questions before the break? Okay, 10 minutes of break. Let's be here in 10 minutes. Efendim? Buyurun. Evet. Ya, ne zaman gelmiş bu kargo? Alo.
Bana ulaşamadılar.
Süt de var istersen. Meyve suyu içmezsen süt var. Süt bitmiş şeyde. Sütüm var.
Bana bir şey olacak ama o çocuğun başı belaya girecek. Çayrola şubesine nasıl yapmıyor? Yok öyle ama yani Darıca'da var, ben Darıca'dakiler yapabilirim, bunu yapıyorlar. Gelmeden geldiler, Çayrola bu arasında bunun genel çalışmacı. Gelmeden efendim? Öyle Sürat Kargo böyle çalışıyor. Tamam, ben ulaşmaya çalışayım bakalım ama bugün çok işim var. Hocam, müsait. 7 tane sekreter var, orada yerinizde yoksunuz diyor ya.
Soru soracaktım ama.
Derste niye sormuyorsun? Cevaplamıyorum. İyice soracaksın. Nerede oturuyorsun sen?
Buradan
Uyuyanlar arasında mı?
yok hocam.
Uyuyanlar önünde mi?
Uyuyanlar gibi.
Sonra tamam.
Dün bir soru sormuştum da onunla alakalı. Şimdi hocam ben bir abstract class tanımladım. CSE diye. Ondan bir derived class tanımladım.
Ha.
Şimdi ben abstract class'ın pointer'ından bu derived class'ın değerine erişmeye çalışacağım. Yani bir
Obje olmadan yapamazsın. Tamam.
burada obje oluşturdum. Bu objeye pointer'ı atadım.
Tamam, güzel.
Şimdi burada bir tane de fonksiyon yazdım. Değer döndüren, içindeki değeri döndüren. Ama mesela
Ne
burada,
döndü? Bir şey dönmüyor ki. Void bu.
buraya hocam ne yazarsam yazayım kabul etmiyor.
Ama
ne
bu
yazmam
void.
gerekir diye soracak.
Bir de şimdi bak. Buraya bir şey yazamaz. Ya bir şey return ne void diyor bu. Bir şey yaz, ondan sonra göster bana.
Şimdi hocam şöyle bu drive class bir template alıyor. Aslında yapmaya çalıştığım şey şu. Bir pointer içinde
Sen anlatma bana. Kodun üzerine göster. Bir defa bu void bir şey return etmiyor. Return edeni yaz oraya, bana göster, bak bu compile olmuyor de. Ben sana niye compile olmadığını söyledim. Bu void bir şey return etmiyor bu.
işte hocam benim yapmaya çalıştığım her bir drive class'ta onun return type'ını değiştirebilir miyim?
Olmaz ki öyle bir şey.
Olmaz.
O zaman derived class'ın interface'ini değiştirmen lazım her seferinde.
Çünkü
void pointer return et. Tamam mı? Void pointer return edersen istediğini return edebilirsin o zaman. Ama onu çağıran kişi ne return edildiğini bilmek zorunda. Anladın mı hocam? Ya ama C++'ca olmaz o. Void pointer return etmek C işi olur.
anladım hocam.
Tamam.
Sana diyor. İşte şu içine sok. Çantana diyor. İçine mi sokuyor? Bana mı? Niye olmadı? Sarsaydı. Su geçiriyor musun? Geçiriyor mu?
Geçirme.
Herhalde. Laptop var için. Herhalde.
Evet. Biraz geçirmiyor. Bunlar belki. Bana şey olduğu için burası. Bunlar falan gösteriyor.
Aşağı. Laptop poşeti falan sıkışıyor. Poşet vermiyorum çantada. Yavaş açsın. Güvenlikten ağlayalım. Laptopsuz geçirmez mi? Ben mi o geldi? Ha. Üç tane yarısı kadar piyasasını atacağız. Alt tanesi 3 kere piyasası. Başta. Normalde küçüğünü mü büyüğünü mü? Tekinin küçüğü büyüğüdür. Piyasacı falan düşünmüş ama Logan var.
O mantığı o yani. Şunu aldım. Bunu aldım. Bunu aldım. Başladım.
Bir çalıştım. Bir de iyi gidiyor var ya şu an. Yani şu an müzik yok. Başka bir şeyler. Oyun yok. Şu an şöyle yaptım şu an. Yapacak bir şey yoksa ya işte 2 saat spor yaptım yani. Başka işte son yapmadan 200 saat böyle 100 gibi 241'e baktım. 2 saat falan. O da biraz tutmadı. Hayatıma gelecekler. 3 kere kontrol. Bir şey var bir şey. Çıktı bir şey. Burada şey yap. Bir dakika. Şimdi bizim raflar var. Burada falan bayağı bir çay var. Çaylar abi şöyle izleyin. Şöyle. Geçen de 3-4 tane lanet satılmış şöyle. Gözü görününce şey kesmiş. Azıcık ucu gözlükte. Ben gözsüzden gösteremedim. Tamam. Sok.
Bak bu.
Burada tek var gazı bayağı gitti. Sanırım var. Kapatmalı. Bundan almak lazım. 120 lira aldım. Oldu. Bu da garip var. Ha. Bravo. Photoshop duruyor baksana. Photoshop gibi duruyor. Photoshop gibi. Pardon. Duruyor sandalyenin üstünde. Kadın Photoshop'lamış. Burada Allah daha uçuşundan yazsa. 2 kat parası var, özlem hocam. Sağ ol. Litre su kaç lira oldu? Kaç litre? Abi borsa bırakılır. Abi de doğal mineral suya tutulur. Senin kadar oldu. 12 tane. Para 55.
Bilmek lazım ki nasıl. Ulan zaten 3 lira 5 lira alıyorsun yani. Tek olsa öyle de. Bir de şey kötü oldu yani. Kuşları var, bir şey var. Zeyn Hoca gibi çıkmış yok. Lider. Erdoğan mı var o?
Öyle olacak bir kodu oluşturuyor. Ona ben size göndermek. Ne tam böyle şey yapıyor.
Okay, so basically basically what we do is this. When I say unique PTR, okay, let's say I have a unique PTR, an integer, okay, I PTR new and integer 7. This is what's going to happen in my memory. Okay, in my memory, I will have this object IP. This object IP contains an integer pointer. Now I got a new integer and it is pointing to that one. Okay, but if the scope goes out, if IP is killed, okay, this destructor comes in and say that I am going to delete whatever I am pointing to. Okay, I am going to delete whatever I am pointing to. So I am fine. So for this new, although I didn't write any delete operators for this new, but remember what was the rule? For any new that you use, there should be a delete, right? So this case, I didn't write any deletes, but it still works. Why? Because when this IP goes away, when it is dead, when it is killed, it kills the pointed memory location by default. Okay, it's nice. Okay, it's nice. Yes.
Can we send a 2D array to this unique pointer?
Can you what?
Can we send a 2D array?
You mean assign?
Can we assign a 2D array?
Why not?
Unique pointer, this unique pointer.
Well, I mean, 2D array is you mean 2D array from pointer of a pointer?
Yes, yes.
Sure, why not? It's a pointer, right?
But how the structure will work if a 2D array, if we assign a 2D array? Because we have to...
Well, of course you should. I mean, if you do this integer k, if you do this address of k, so you are shooting yourself in the foot, right? What are you doing? You are saying that this unique pointer IP is pointing to some integer position, okay, and I have created it myself. So whenever this IP dies, kill this integer too. But that integer doesn't live in the heap, right? So of course this is not going to work. You are going to get a crash out of this, right? Segmentation fault or something like that. Okay, so I mean, you just invented another way of killing yourself using C programming language, which is not that difficult to do. Okay, so I mean, don't expect this to work miracles for you. Do it something right. So I am doing this new operator and integer. Okay, and so okay, good. So in your classes, if you need to use some pointer, and that pointer is going to point somewhere, and using the heap position, using the div operator, okay, I suggest you use these unique pointers, because when your object dies, it's going to kill this IP in it too. When the IP is killed, it will kill whatever it is pointing to. But there is a problem in this approach. The problem is this. The problem is this. Okay, the same picture, let's put it aside like that. Okay, now I am doing this. Another unique pointer, unique PTR, integer, okay, IP2 and IPE. So what kind of picture would I get out of this? I will get something like this, right? So IP2 is here, IP2 is here. My copy constructor will copy everything inside this IP, including that pointer. Now this one is pointing to the same location too. Okay, So when IP dies, it's going to delete this integer. When IP2 dies, it will try to delete the same integer, but that integer is already dead. Okay? So the problem is again the shallow copying problem, right? And I don't want to make a deep copy of it because this is a pointer. This is not the object itself. So what am I gonna do? Okay. The thing is this. Okay. The thing is this. Okay. Maybe I can do this. Okay. I will make my copy constructor private. I will make my assignment operator private. Okay. So this will not work anymore. So you guess the name, right? What is the name? Name is a unique pointer, right? Unique pointer means that whatever I am pointing to, nobody else points to. Okay, I am the only pointer that points to that object. So how do I satisfy this? By preventing anybody else, from copying my content. So I made the copy constructor of the unique pointer, and I made the copy constructor of the assignment operator of the unique pointer private. So when you write this, okay, this will not compile because these two are private. Okay, these two are private. Other than making them private, tell me another way of disabling these two functions, copy constructor and the assignment operator. Delete equals delete, right? And you say unique pointer something, delete, right? This will delete the copy constructor, and this will delete the assignment operator. This is better, okay? This is better than making them private. Okay, yeah.
You put static and it works as well.
If you put static to where?
Before the function name, but it's not.
There are no static constructors. Constructors cannot be static. Okay. Okay, so I kind of achieved it, unique pointer, and it works. Okay. So whenever you made a new object using the heap, using the new operator, if you are not going to point to the same object using different pointers, then use a unique pointer which is available in STL libraries, unique pointer. Okay, this is how you use it. Let's see what kind of functions we have. Okay, pointer, constructor, destructor, operators, assign. Well, the operator assignment is available. We are going to see what it is. See, I have this one, release. As a unique pointer, I can release my pointer. I am not pointing to that anymore, but without deleting it. You understand what it says? I can release my pointer. I am saying that I am not pointing to that object anymore. So when I die, I am not going to kill it. So this is how you assign and release. First, you assign it to somebody else, then you release it. Okay? And maybe you can swap your pointers with somebody else. And you can get the pointer that you are pointing to using the get, etc. These are the operators that you have overloaded already. An index operator is available with the pointer starting from what? Oh, I don't have it anymore. Well, yeah, originally we have this index operator. Remember, with the pointers we have the index operators, and these are the comparison operators that are available. Okay, good. So that's the unique pointer. So let's move on. I'm going to introduce something else. The idea is this: a shared pointer class. So a shared pointer is going to do this. I can assign one shared pointer to another shared pointer. Okay. What is the big problem in this case? If I am pointing to the same object, when I die, the object will die too, and the other one will be using the dangling pointer. But this is what I'm going to do. I will count how many pointers are pointing to me. Okay. So this will be it. If I have a new object in the heap, this is my object. I have a pointer that points to this one. I have another one, it points to this one. I will keep a count. It says 2. This one says that 2 pointers are pointing to me, okay? If I kill this one, this 2 will become 1. And if I kill this one too, this 2 will become 0. Then I can kill this one because nobody is pointing to it, okay? This is how shared pointers work. They count how many pointers are pointing to that object, okay? When the count reaches 0, this object is free to die, okay? That's the shared pointer. It's a little bit more complicated than the unique pointer. That's why I'm not going to show you how the internals work. It is not that difficult, but I mean, it is already implemented. But that's how the shared pointers work, okay? This is what I'm going to do. Very similar to unique pointer, public part, okay? The copy construct, the constructor itself with a pointer, the destructor, the reference operator, plus operator, but I have the copy constructor and the assignment operators defined. Whenever I assign one shared pointer to another one, I will increment this number by 1 when you do the assignment or when you do the copy construction, okay? So whenever you kill one of these pointers, you will decrement that number by 1, okay? When that number reaches 0, you delete it automatically. So this is much more useful than unique pointer, a little bit more complicated, much more useful, and a little bit more expensive too, right? Because whenever you do any pointer assignment, you need to increment this number. So pointer assignment, pointer copying becomes a little bit more expensive, but I mean, it is well worth the cost if you are not writing very tight CPU time-sensitive code. This is a good solution to use all the time. Shared pointers, okay, shared pointers, and this is how it works. Actual pointer is here, okay. Actual object is here. There is a control object which controls this actual object, and this shared pointer actually points to this control object, okay. I made this, for example, let's say I made a new object, shared pointer, I point into it, okay, and I will call this doIt function, call by value, right, call by value. P2 is a copy of P1, that's why P2 is going to show this one too, okay, P2 is showing this one too, so the reference count is 2, actual object doesn't know anything about this, okay. Then inside this function doIt, I make another one, P3, and I will assign this P2 to P3. My picture is now this, okay? So 3 pointers are pointing to the same object. And the count is 3 now. So I executed this line, and I executed this line. When I execute this line, P3 will die, right? When P3 dies, okay? It goes away. When it goes away, it will decrement this count by 1. So reference count is 2. And when I am done with this function, okay, when I am done this function, when doIt, the function doIt is done, it's finished, okay, then this P2 will go away because P2 is a local object of this function. It will go away. It is in the stack. When it goes away, okay, it will decrement this one, and when this P1 dies at the end, this will die. When it dies, this will decrement this count by 1. When it sees that I decremented and the count is 0, then in that case it's going to delete this object too. So the last object that dies and makes this reference count 0 is responsible from making the object, making the reference count 0. Okay? Shared pointers. They are much more flexible than unique pointers. You can copy them as you like. Shallow copying is done, right? These are all shallow copies. Shallow copies, they're all pointing to the same object, okay? But that's okay, why? Because when I delete this one, it knows that there are other people pointing to the same object, okay? So if we are using this shallow copy thing, we are using this shallow copy thing in our advantage. Question for you. What is wrong with copying the actual object all over again, okay? Make a deep copy all the time. What is wrong with it? So don't do the shallow copy, do the deep copy all the time. What is wrong? What is wrong making the deep copy all the time? Making deep copy means that everybody has their own objects. When they die, they can kill that object, and that will solve the problem. Yeah.
There is no single object and performance issues.
Yeah. Well, you are using lots of memory, right? When you do the, okay. See what I do here. When I call this doit from this function, I am just copying this pointer p1. I am not copying the actual object, okay? It's the same object. It's the same object, okay? So since I am not copying it, I am just fine. The other thing is this. These kind of functions are very useful. A function returns a shared pointer of, let's say, a string. Okay, f. I don't know what it does, but at the end it says that, okay, return shared ptr string new string, a new string. I don't know what the parameters are, but I make a new string, I just return it. So who's going to delete this new? It's a very dangerous thing, right? Whoever receives this one should be responsible for deleting it, but in this case I don't care because I am returning a shared pointer. If somebody copies it, then it's fine. If they don't copy it, this one will die and it will kill the string too, right? So these kind of functions are very useful. A function, instead of returning a pointer, it returns a shared pointer. So deletion is done automatically. Yeah.
Why does it die if no one copies it?
What?
Why does it die shared pointer if no one copies it?
If nobody copies it, that object has to die, right? This is a temporary object it returns. That object dies. When it dies, the destructor has to be called. When the destructor is called, it's going to kill this string. Okay? I made a new object with this. This is a new object, right? Shared pointer. It's a temporary object. I am returning it. Since this object, it has to die someday, right? When it dies, it will kill the pointer it is pointing to, unless somebody else is pointing to it.
It will die when the scope that's called the f.
It will die when I do this. If I call this function without assigning it to somebody else, it will return that object. Since nobody has copied it, since nobody is using it, it will die, right?
Right after that line?
Yeah. Right after this function is called. What does the printf return? Printf something. What does it return?
Number of characters.
So what happens to that integer? It returns an integer, right? What happens to that integer? It dies, right? It's just a temporary thing that you return on. Remember our activation record in our stack? There was a portion in my stack that is reserved for the return value. That value will go away, it will die. So this one will die as soon as this function is done. Okay? But if I copy it using assignment operator or the copy constructor, then somebody else will be pointing to this new string, okay? Even though that returned object will die, this one will not get deleted. So this is the most useful part of this shared pointer or the smart pointers. Okay, so it prevents most of the memory problems related to using heap, new and delete operators, dangling pointers, memory leaks. If you use them right, okay, if you use them right, it will make your pointer life a lot easier than compared to regular C pointers. Okay. Good. Did I miss anything here? No. Actual object is this shared pointer class. Yeah, we did that already. Okay. So shared pointer C++. It is already in the C++ standard, C++ 11 standard. This is nice, right? Remember, I always make vector of pointers of something. Don't make it. Vector of shared pointers of things is better. Why? In this vector, I can put my object, another object, doesn't matter. When this vector dies, it kills its element one by one. When their elements are killed, right? When their elements are killed, then they will kill their pointed elements if nobody else is pointing to them. Okay? Good. So try to use this all the time. It is. Everybody knows it is standard. It is not something somebody has invented and it is making it available. It is part of the C++ standard after C++ 11. And if you look at the C++ shared pointer, do I have C also here? Where is C also? Yeah, shared pointer. Okay, so shared pointer is this, very similar to unique pointer, but it has some other. See this one, the use count. You guessed it, right? It returns the number of shared pointer objects referring to the same managed object. So how many other pointers are pointing to this to my object, right? It returns you that one, use count. Okay, or you can say after C++ 20. Am I the only one that is pointing to this? Unique. Okay. This one, remember, pointers are, we use them as like a null, 0 or not, right? Remember in C, we have the null. If a pointer is null, I can say if PTR, etc., not PTR. Of course, this is not a pointer, this is unique pointer. Whereas there is this operator bool. You can say if unique pointer kind of thing. It returns you a boolean, and that boolean is true if you point to something. Otherwise, it is false. Right? And what else? These are already done. For some reason, I don't know why, there was not index operator in C++ for shared pointer. Unique pointer there is, but for the shared pointer there was not. I don't know. I think there was a complicated issue. Writing this was complicated. I can guess what it does, but you can always get the pointer out of the shared pointer if you like to. And if you like, you can delete it yourself, but that will give you a serious trouble. Okay, don't do that. Okay, this idea sounds nice, but you may end up, let's say I have a linked list. I have an integer, and remember how we do the linked list? Let's say this is my node. And usually I write a node pointer here, right? That node pointer points to the other one. Now I don't do that, okay? I do it this way. I say that, okay, I will have a shared PTR and node, right? A node shared PTR. So this will point to the other node. And this can point to other node and etc. Right? I can do this, no problem. I don't have to delete anything. If the other node is pointed to by something, then it's okay. Otherwise, it will get deleted. This is fine. This is good. It works very nice. But what happens here? And nobody is pointing to this node. Okay. This is called circular pointer link, and it's a serious cause of memory leaks with the shared pointers. Nobody is pointing to this one. They are pointing to each other. So the pointer count for this one is 1, 1, and 1, right? At least 1. So this is a memory leak, right? This is a memory leak. That's not a good thing. There are algorithms to detect it. Is this a circular reference thing going on? Can I detect it or something like that? So you need to be careful about this kind of a possibility. With the linked list, it can happen, especially with the double linked list. Single linked list is possible too. Okay, we use this structure all the time. Okay, so how do you prevent this? Don't use shared pointers with the linked list. That's not a good idea. They have invented this. What?
Make sure one of them has true, maybe.
How are you going to do that? Always, okay. Always keep a head pointer, shared pointer, pointing to the one of them. Make sure this. But, I mean, by some accident, by something, if this happened, you will never know that this had happened. It's an error. Okay. Some people suggest they use this weak pointers. Weak pointers. Where is my weak pointer? Yeah, weak pointer. Weak pointer is like a shared pointer, but it doesn't do it says that, okay, it's a smart pointer that has a non-owning reference to an object. I am holding a pointer to that object, but I am not owning it. I am not incrementing the value of it. So if you keep one of your pointers as weak pointer, then you are fine. Okay. So weak pointer doesn't increment. It behaves exactly like shared pointer, but it doesn't decrement the value of that object. So it looks like nobody is pointing to that one. Okay, good. So that's I guess that's it about the smart pointers. So use smart pointers appropriately as many places as you like. Try to use them instead of the pointers all the time. That will make your life a lot easier. Good. Am I missing anything? I guess not. If I don't miss, okay, so this is a nice comparison. Both will perform automatic deallocation. UniquePointer only allows one pointer to an object at a time. That's why it's named unique. Okay. Shared pointer allows any number of copies of the pointer. Okay. In Java, they say that there are no pointers. Okay. In fact, they have pointers, but they call it references, and those references are in Java. The references are smart pointers of C++. Okay, they say that they don't have any pointers. They have pointers, but their pointers are smart pointers. That's why in Java there is a new operator, but there is no delete operator. Okay, you can't use delete. There is a new operator, but there is no delete operator because only a pointer that can have is a smart pointer, not the other pointers. Okay. And other languages like Python or C#, they use this idea too. Good. Okay, so one last thing before I declare you experts of C++, I will talk about move semantics with the C++ 11. Okay, let's start talking about them. Yeah, before that, before that, remember at the beginning of the semester somewhere I told you that there are two operators that I will not talk about. One of them is this operator. The other one is this operator. Two of them. Okay? These are called member pointers. They are pointers. They are member pointers. They are only used for pointing to elements of classes, either data members or the function members. Okay? They are called member pointers. They are not regular pointers. So they need some kind of an object to work with. So it has two components, an object pointer and a member pointer. And from time to time you are going to see that they are kind of useful, and we are going to see how. Okay? Since this course is about object-oriented programming, but I don't want to ignore any part of C++, from time to time it might be possible to use them. Okay, let's look at this one. So this is data member pointer, function member pointer. Okay, for a class I can write it this way or that way. We already know that, right? Class object, class pointer, okay, address of that object, it works. This one says that in this object, in this class, okay, I have a data member pointer. I have a data member pointer and I can assign it. Or I am calling this function of this class on this object. Okay? Remember, this is not PTR. With the PTR, you will say PTR and some data member and assignment. This one says that, okay, this one says that here, okay, I am saying that with this object, I will call a function member and feed this. Okay, let's see an example. I copied these, I have stolen these slides from this gentleman, Zoltan Porkolab. Does anybody read whatever this language is? Polish, maybe? I guess Polish. I am hoping that I am reading his name right. Okay. I didn't thank him personally with the email, but I mean I am thanking him here. Okay. So let's look at this class. A date class. Regular date, year, month, and day. Good. I have my setter. I have my getters. Get day, get month, and get day. And there is a print function. Print function is kind of a problematic. Why? Because the way we print in Europe the date and the way they print the date in USA is different, right? In USA, they use this format, right? They use this format. What kind of format? They put the month first, then a slash, then the day, then a slash, then the year. In Europe, usually we use this one, 23rd of month 3 of 2020, right? So I like this print to change its behavior, depending on what function I called. If I call this function US, the behavior of the print will be like this. If I call this function HU, it is Hungary. Oh, okay, this guy is from Hungary, okay? It's HU, then it's going to print it like this, European style. Okay, so sorry Zoltan, I called you Polish. Paul. Do we call them Polish or Paul? Polak. What? Le, really? Le is a race, right? It's not. It's a race. Lehçe is a language, but we don't call the Polish people Le all the time. Really? I don't know. I am sorry, Zoltan. I don't know what I am talking about. Okay. I changed his name. I changed his nationality. Now we don't know what language he speaks. Sorry. We do that all the time. Okay. So let's look at this one. Okay. So look at the implementation of this HU and US. What? What is this? Let's go back to this one. So and say that I have year, month, and day. I have 3 pointers here, P1, P2, and P3. Okay? P1 is an integer pointer, but it's an integer of date class. It's not a regular integer pointer. Remember what they said about this? Remember what we said about this operator? It works only for the member data and member functions. So this is a member data pointer of date class, and it has to be integer. So P1 can point to year, month, or day because all 3 of them are integers and they are part of this date class. Okay, specialized pointer. So you might say that why don't we use a regular pointer, integer point P1, integer point P2? Yes, you could, but in that case, your solution would be too general, and these are very small pointers. Okay, these are not as large pointer as the regular pointers. Okay, so I can assign P1 the address of this year or month or day. That's what I'm doing here, right? I'm assigning P1 the address of date month or date day or date year. Okay, or with the HU I can doing this. So P1 in this case becomes year, P1 in this case becomes month, right? P2 is day and P3 is year. So if I am going to print something, where is my print? So prints this. Print away prints, okay? This arrow star P1, this is how you use it, right? This is my pointer, my object. On top of my pointer, I am going to give you another pointer of an object. Okay, it is P1, then print P2, then print P3. The meaning of P1, P2, P3 will change according to which function that you had called before, HU or US. Okay, if I called HU, I will print this one, 2017.4.20. Otherwise, it will be 4/20/2017. Why? Because the meaning of P1 is different in this both cases. Okay, so my constructor sets these. Your year, month, and day is the same. It doesn't change. The meaning of print changes. Why? Because P1, if you called it HU before you call this one, okay, the meaning of P1 is year. But in this case, the meaning of P1 is month. Okay, so there's one way of using member pointers. How about the member pointers with the member functions? Okay, in this case, I will have exactly the same class, but this time I will have 3 function pointers, but these are member function pointers, not general class, general global function pointers, but date class function pointers. And when I call this HU, G1 becomes date get year, get month, and get day. But if I call date US, that will be it. Our print function says that call G1, G2, and G3. It will get the appropriate year or month or day, depending on what you called before, and it will print it out. Okay, so that's the member pointers, class member pointers for both functions and the data members. Okay, one of them is for the dot operator, dot star operator. The other one is regular arrow operator. Okay, it is arrow star operator. Okay, I am not spending much time on it. I did not see many employment of this class in any code that I had seen, but since these are part of the language itself, I just spent maybe 10 minutes on it. I told you about it, so that you know everything that I know about C++. Okay, any questions? Okay, if there are no questions, I guess that will be it. Tomorrow I will do this one more thing. I will do this move semantics with C++. No, not this one. Where is my move one things? Yeah. Yeah, well, no. I will continue on this. I will continue on this slide, okay? Remember L values and R values? Okay, C++11 have some things to say about L values and R values, and it makes them a little bit more controllable and flexible. At the end of the class tomorrow, you will be able to, well, this is nice, right? The C++ committee, which is the committee that to set the standards of C++, they say that, okay, we are not about the software code safety, okay? If you like to shoot yourself in the foot, we will not prevent it. Go ahead and do it, okay? So that's good. So tomorrow, you will be able to understand what this kind of code is. You already know what this is. What is this? This is a class S. This is the constructor of S. This is what? Copy constructor of S. This is the move constructor of S. Copy is move moves. Okay? Copy assignment, move assignment. Okay? So copy, as the name implies, copies makes a copy. Move says that, well, you are going to die anyway. I am going to steal your resources. Right? Remember this one? If a function f returns a very large object, and I like to assign it to a vector v, right? If I am returning a temporary vector, and that vector is 2 gigabytes large, I don't want to make this copy like 2 gigabytes of copying. Whatever this f is returning is already going to die, right? So why don't I steal your pointed object from yourself, right? So this is going to be a move assignment operator, and this is how you do it. And I can do the same thing with the move constructor. So remember our big 3. Now big 3 is going to be big 5. Big 3 is written this way. Well, I write it this way. Okay, capital letters big 3, big 5 is like this. Big 3 is bigger than big 5 actually. Okay, so with C++11 we have big 5. Okay, tomorrow. See you.